from this decision space. So these points in the objective space is called Pareto optimal front, and in the decision space, this is called Pareto optimal solution. So actually we visualize those points from the objective space, but actually those points in the decision space are called Pareto optimal solutions. Okay, so that is the point. So at first we visualize those points in the objective space and determine those solutions in the decision space. So next, the set of all Pareto optimal solution in the objective space is called the Pareto front. So this is your Pareto front. And the Pareto front shows the trade-off relation because these are non-dominated points. Non-dominated points. So that's why there's a trade-off relation between those objectives. Like this. So these three are Pareto front. Clear? Now, if we consider a very simple example here, we just look. So suppose you have two objectives. One is maximizing, other is minimizing. Here, not both are maximizing. So suppose we consider this is a minimizing objective. And objective space, we are considering some 6 different points. So you can easily compare because maximizing, this is minimizing. So obviously, if we compare 1 and 3, 3 is better than 1 because this is maximizing. So this length is more, but this is minimizing. So this height is more. That means 3 is better than 1. Similarly, we can compare 5 and 4. So out of those 6 points, these 3 points are dominated by any one of those 3 points. But these 3 points are non-dominated points. They are better with respect to one objective, always. So that by this simple mathematical representation, you can understand, I think so. So these are non-dominated front. So in general, so for simple visualization, so if your objective region or objective space is like this. So this is your objective space. Now, for different pair of functions, maybe max, min, min, max. So what is the general Pareto front representation? So if both are minimizing objectives, so obviously this lower envelope, that means towards the origin, that envelope gives you the actual Pareto front. Similarly, if it is min max, F1 is min, F2 is max, in this left upper corner gives you the Pareto front. Similarly, if it is max min, so obviously the right lowest corner, this gives you the Pareto front. And if both are maximizing, then this is your Pareto front. Okay, this is general concept. Okay, so for Pareto optimality, because here the next target is 30, there will be. Okay. So that means when we want to determine the Pareto optimal solution, so because here our main target is how to determine the Pareto optimal solution. So how to determine that Pareto optimality? So obviously, conceptually, a solution is Pareto optimal if no solution dominates it. That is the first point. Set of all Pareto optimal solution in the variable space or decision space is called Pareto set. And set of all Pareto objective vectors is called Pareto front. So there are two. One is decision space, one is objective space. Objective space, it is called Pareto front. Here it is called Pareto set. Next. So obviously there is a one-to-one mapping that already I told you. Okay. So now the next part, how to solve a real multi-objective optimization problem. So what are the steps for solving the multi-objective optimization problem? So obviously, these 3 points are most important points when you want to design an algorithm for multi-objective optimization problem, or maybe any mathematical techniques you want to design for solving that problem. So first is all the Pareto solution or Pareto objective vector are well diversed. So that means you are design a front with some discrete points. They are well diverse. They are not clustered in some zone, not clustered in some other zone like this. It's very well diversed. You should maintain that diversity in your solution. The second one, obviously they are convergent in nature. That means they are close to the true Pareto front. So if we consider two conflicting objectives, theoretically there is a true Pareto front. In general, you cannot determine that true Pareto front, but you can easily visualize, because if these two are maximizing objective, here your true Pareto front is there. You can visualize it. But so obviously your target is all the solutions your algorithm generating that towards to the true Pareto front. That means that those are convergence in nature. When we use some meta-heuristics algorithm for single objective also, the major concern is whether it is converging in nature. Maybe there is no convergence, theoretical convergence, but target is numerically you can show your solution is approaching towards the global optimality. So the convergency, that means it should be close to the true Pareto front. And it covers to the whole spectrum. Because this is your decision space and this is your objective space. Objective space has many points, but only one small portion of Pareto front you are generating or your algorithm is generating. So that means your algorithm is not properly justifiable for your solution, for the solution. So obviously your Pareto front, because both are maximizing, means Pareto front is upper right corner. Visually it is this. But it is only one small part of that. You cannot consider that is a good solution. So these three, that means when we design any algorithm or any technique for solving multi-objective problem, always your concern is these 3 points. Clear? So that means with respect to these 3 points, if we claim your algorithm is performing better with any other algorithm previously designed, so obviously you will have a good solution or you have a good algorithm. So that is the target. So visually you just look. So suppose we are generating 2 different solutions by 2 different algorithms. One algorithm generating some solution points, those are represented by those green points, and another algorithm representing some points, those are those red points. Red or pink? Red. Okay. So now you compare. With respect to all those 3 concerned, that means all those 3 points, which set of solutions are good or better? With respect to convergence, because this is your true Pareto front, this continuous line is your true Pareto front. So both are minimizing objective. So obviously green points are closer than red points. So obviously with respect to convergence, green points are better. Now with respect to diversity, we look, red points are clustered in some zone. But green points maintain well diversity. Between any 2 solution point, they maintain the similar gap. You look. So that means green solutions are as well as well diverse. So diversity is preserved. And again, in some zone, there is no red solution. That means they are not cover the whole front. They cover some part of the front. So with respect to all the 3 previous comments, green solutions are better than red solutions. So obviously, these are better solutions, these are bad solutions. So that is the target. So that means when you design any algorithm, so obviously your target is how to design the Pareto front or Pareto solutions which are well convergent, well diverse, and covers the whole front. So this is the exercise. When we want to design any multi-objective algorithm, the exercise is this. Okay. So now come to the real problem. So there are many real decision problems. It may be in engineering, maybe in management, or any real decision problems. Maybe engineering design, environment and energies, telecommunication, control theory, transport logistic, many other areas. So all are in most of the areas any real problem. So suppose if we consider any engineering design problem, mostly they are concerned with two things: cost and quality. So at least these two objectives are there. Maybe there are more objectives. Similarly, all other areas, there are many conflicting objectives, not only one objective. So most of the real applications, there are more than one objectives, and those objectives are conflicting in nature. So that means once you design your engineering problem some mathematical optimization way, so obviously there are multiple objective problem. So that is the main concern. So similarly, there are some academics problems. So why this academics problem is needed? So suppose tomorrow Professor Saha will deliver some new meta-heuristics algorithm. Like maybe I forgot the name. So, but how to compare his algorithm is little bit, at least little better than the previous algorithm, not much better, say. So obviously, with respect to if we apply it in any single objective optimization, with respect to convergency, with respect to complexity, obviously he should prove his algorithm is better than the previous. Otherwise, he cannot claim his algorithm is better performing. Clear? So here also, if we design a new multi-objective algorithm or multi-objective evolutionary algorithm, how you claim your algorithm is performing better than the previous algorithm? At least 1, 2 algorithms, then actually you claim, okay, so it is better. So because there are many algorithms. So for that, some academician already designed some multi-objective problems. So these are like ZDT, CDP. These are basically name of some scientist or some mathematicians. They designed that algorithm. So ZDT is Jitlar, Dev, Kollanmoy Dev. I think maybe some of you know that NSGA2 is one of the important evolutionary algorithm. So that is designed by Kollanmoy Dev and his group. So this is Jitlar, Dev and someone. So in this way, they design one engineering problem. That's why it is called ZDT problem. So that means once you design a new algorithm which is maybe parallel to NSGA2 or multi-objective GA, then obviously you should compare your algorithm with that problem. So whether it is better, little better at least than NSGA2. So then you claim. So that's why these are called some academic problem, because there are many discrete problems like multi-objective assignment problem, spanning tree problem, TSP. If time permits, I will show you in this area. We already published some paper. These are always NP hard, because I think some of you have the idea NP complete, NP hard, and so on. So these natural problems, TSP, quadratic assignment, vehicle routing problem, these are very famous problems in operations research domain. So if we consider multi-objective TSP, multi-objective assignment problem, vehicle routing problem is much more harder. Single objective TSP is always NP hard. So obviously multi-objective is much more harder, obviously. So there are some sources where you can collect some data or some by which they can design some problem. Source code is there for this multi-objective TSP, multi-objective quadratic assignment problem, that is available in openly available. So once you design a new code for multi-objective TSP, so obviously you should compare with that. Otherwise you cannot claim your algorithm is performing well. Okay. So next. Now the solution part. So when we want to solve any multi-objective multi-objective decision making problem or multi-objective optimization problem, what is the thumb rule? So generally, people design several optimization technique or optimization algorithm by considering these three concepts. Because because in real system where you cannot design any theoretical optimization algorithm for solving your problem, then always your target is whether your decision maker is happy or not. So one decision maker gives you a multi-objective problem. You give the solution to the decision maker. If it is acceptable to the decision maker, then fine. This is your job as a maybe mathematician or as a engineering design analyst or like this. So that means once you design the multi-objective optimization problem, you want to solve your problem, then the thumb rule is there are altogether we can divide this into three types of solution technique. One is prior approach, another is posterior approach, next one is interactive approach. Conceptually, you just look, what is your prior approach? Prior approach is decision maker gives you the concept or target prior to the solution. That means, suppose your Pareto solution space is like this. So decision makers initially gives you, I am interested here, I am interested in here. So that means he gives you the target forcefully. That's why it is called prior approach. I am interested those solution points which are that left uppermost corner. So that's why it is called prior approach. Decision makers gives you the preference before the resolution of the process. Clear? So that's why it is called prior approach. Another is posterior approach. Decision maker gives you the solution. He don't have any interest. You give the solution, then he or she interact. Okay, you give this solution. Well, this solution is okay, but I am not interested with this zone. You may check other zone. So maybe you can find some good solution there. So that's why it is called posterior approach. Clear? So at first, decision maker gives his problem to you. You solve as per your algorithm and give the solution to the decision maker. Then decision maker interact. So that's why it is called posterior approach. Then interactive approach. Decision maker gives you the problem, you solve. After some resolution, after some iteration, decision maker may interact. You are converging in this area, but I am not interested in this area. So you should change your algorithm. You can move other area. So that means that's why it is called interactive approach. So most of the algorithms are designed either any one of these three techniques. Obviously, there are lots of pros and cons. Some approach gives you better convergence. Some approach gives you better diversity. Some approach gives you the better covering the whole spectrum and so on. So obviously, different people approach different aspects, different ways. There are several algorithms. There are conflicting those algorithms, but most of the algorithms are designed by using any one of these three concepts. That is the main issue. Okay. So solution methodology, this is similar to the single objective problem. But here, first, there are some classical approach. Classical approach are mostly transformation of multi-objective algorithms, multi-objective problem into a single objective one. Once you transform it into single objective, so obviously there are lots of classical approaches that already I told you, branch and bound, dynamic programming, geometric programming, many ways you can solve. So by those techniques, you can easily solve. So that's why it is called classical method. On the other way, approximate method, that is much more applicable to the real multi-objective problem. So already I told you, some are handled by some heuristics approaches, some are handled by some meta-heuristics approaches. So those are problem-specific heuristics. That is already I told you. Otherwise, meta-heuristics, most of the meta-heuristics gives you a population of solution, not a single solution. That is the major advantage of meta-heuristics, because in multi-objective optimization, we look for a not a single solution, it's a population of solution, set of solution. So that's why population-based algorithm obviously much more better approach for solving multi-objective optimization algorithm. Okay, so conceptually, the goal is that already, yes, just this slide. So already the goal I have already defined. So yeah, the three things are important. One is better convergence, better diversity, and better covering the spectrum. So these things, and obviously this is better diversity is good. Here convergence is good, but it's not covers the whole spectrum. And altogether, this is the best. So this is the final thing. Maybe after tea again we can discuss. Okay. In between, if you have any questions, the tea.
Hello, sir. Hello. Dear participants, we are taking a break of 15 minutes for tea. After tea, we will again meet. Please join, sir.
So, welcome you to the next session of this lecture. So, next slide. Okay, so already I told you, so there are three aspects. One is prior approach, another is posterior approach, another is interactive approach. So sometimes it is represented in this way, non-preferential method. So at first I give you the idea, there are some classical approach. So that already I told you, in the most of the classical approach, they transform the multi-objective into single objective by some mathematical way, and then they can solve in the classical technique. So first, what is the concepts of non-preferential methods? These methods do not assume any information about the importance of the objectives due to the absence of the decision maker. So here decision makers is not there, that gives you the problem and you solve fast. But heuristics is used to find the single optimum solution. So we first transform it into single optimum. They do not make any attempt to find the multiple Pareto optimal solution. So one of the important example is this ideal point method. This is one of the classical method mostly people have used to solve such type of multi-objective problem. So I just give you the mathematically, it's a very simple mathematical form. You just look. I think the simple distance measure. So here, say suppose you have k different objectives. We transform this sum of I equal to 1 to k norm of fi x minus zi star p whole to the power 1 by p. So this is just like the Minkowski's distance measure. So here, if we consider p is 2, this is basically the Euclidean measure. So anyway, so what is the concept? So you just solve, say suppose you have two different objectives. You solve the problem as single objective. So first solve f on x with the same constraints and determine a solution. So that is z1. Again you solve z2. Considering all the constraints, you maybe determine that z2 star, that is the optimal solution. So now you design this new objective, sum of f1 minus z1 square, suppose if you consider Euclidean measure, plus f2x minus z2 square, then square root. It's a very simple mathematical function. So it's a single objective problem now, subject to all the constraints, and then determine the optimal solution. So obviously, if we use this ideal point methods or this type of classical approach, always you will be getting a single solution, not multiple solution. So that's why, though this is a very simple classical approach, you can easily solve the problem in this way, but here, by using your algorithm, you can generate only one solution point. That is the main disadvantage. Similarly, so say for example, you have three objectives, we consider three simple objectives subject to one constraints. We can easily solve this by ideal point method. That means you just look, you solve the first objective with respect to one constraint, you get one solution point. Then second objective, you get Z2 star, then Z3 star. Then by using that method, finally you obtain these Z1, Z2 and Z3. Okay. So this is the concepts of ideal point method. Then prior approach, that is basically here initially the decision maker gives you the preference of objectives. This is my preference. First objective is most important, second objective is next important, and so on. So then there are several approaches like goal programming, goal attainment, lexicographic method. Many approaches are there. That is mostly available in the literature. So you can use those for solving that. So for goal programming, I think maybe this is your syllabus, in MSc syllabus, goal programming method is there. The method is this. There are some goals, you are determining those goals and minimize this function subject to the constraints. Okay. Can you आप बंद कर सकते हैं, बंद कर दो. Okay. Similarly, for lexicographic approach, so here also individually we are considering the goals. That means we first determine F1 star, then using this F1 star you are determining F2 star, then F1, F2 star you determine F3 star and so on. So that's why it is called lexicographic approach. Because you are helping the optimum value of the first objective, you are determining second objective. You are helping first and second objective, you are determining third objective. So that's why it is called lexicographic approach. So all are classical methods, and basically here you transform the multi-objective problem into single objective, then solve. Similarly, posterior approach. This is weighted method. So conceptually, weighted method is you are determining some weight as per the choice of the decision maker. Say suppose you have three objectives. Decision maker first choice is first objective, so you are giving more weight to the first objective, then next objective and so on. Accordingly, you can design your weight sequence, and considering the objective function in this way, W1 F1 plus W2 F2 plus W3 F3 and so on, subject to the constraints, and another constant is added here, sum of the weights should be 1. So then you solve. So this is weighted method, and here the main disadvantage of weighted method, here also you are getting single solution. So if your objective space or your decision space is in convex form, that means it's a convex function, so obviously your weighted method gives you a good solution. Say suppose this is your minimizing objective. So both are minimizing. So obviously your true Pareto front in this corner. So now if we take the weight function in this way, W1 Z1 plus W2 Z2, basically this gives you a line here. And this line touches this convex surface at a point. So that gives you a point on the true Pareto front. That means always you are getting a point in the true Pareto front by considering this weighted matrix, weighted vector. But on the other hand, if it is non-convex, suppose your surface is like this. So maybe sometimes you get a very bad solution. Because obviously if it's a minimizing objective and if this is your true Pareto front, you are getting many solution. That means if we get a line here or here, that solution is much better than this solution. From picture it is very clear because both are minimizing. So that means if your actual front is not a convex form and not a convex function, then this weighted method may fail. Or maybe you get a very bad solution. So that is one of the major disadvantages of this weighted method. So sometimes those classical approaches like goal programming, goal attainment, lexicographic method, weighted sum method, you are getting a good solution, but say one solution if your that objective function or your Pareto front that gives you a convex function or convex in nature. Otherwise, sometimes you may get a very bad solution also. Okay. That is the main disadvantage of these methods. Okay, now come to the evolutionary, multi-objective evolutionary part. So if we consider that the genealogy of meta-heuristics, I think there are several meta-heuristic optimization algorithms are available in the literature. Maybe every day some of the people are producing some new meta-heuristics algorithm. Dung beetle algorithm, harmony search algorithm. So many other algorithms are there. That is, so it started with very early 1950s. So there are many greedy heuristics approaches, evolutionary programming, evolutionary search, genetic algorithm, particle swarm, ant colony, bee colony. So many meta-heuristics algorithms are available in the literature. So now here the purpose is target is how to design a meta-heuristic, multi-objective meta-heuristics algorithm. Is there any unified view of that meta-heuristics algorithm? So obviously, when we want to design a meta-heuristics algorithm for multi-objective optimization algorithm, so your main concern is into three components. One is obviously the first part is problem-specific component. So if we design your problem in a multi-objective optimization, it may be discrete problem, maybe continuous problem, then which type of meta-heuristics works well. So those are problem specific. Whether it is a continuous domain, whether it is a discrete domain, your function is continuous, function is discontinuous, discrete. So many things are there. So those are problem specific component. So here at this present lecture, I am not concerned about the problem specific component. Obviously, the main concern is multi-objective specific component, and the next part is meta-heuristic specific component. So once you know one meta-heuristic algorithm, maybe GA or maybe PSO, whatever it may be, so obviously here the concepts of meta-heuristics part is very similar. So same steps. Say, I think some of you may know the genetic algorithm. So genetic algorithm, what are the basic steps? Selection, crossover, and mutation. These are the three components. So selection strategy, crossover, and mutation strategy. So obviously for GA also there are different types of selection strategies, crossover strategies, other things. But same thing you can use that meta-heuristic components is same here. But so here our main concern is multi-objective specific components. Those three components that already I told you, convergency, diversity, and covers the spectrum of the decision space. So next. Okay, so that's already I told you. Any development process of multi-objective meta-heuristics, there are three components. Problem-specific component, there's design the components of meta-heuristics, design the components of multiple objective meta-heuristics, and implementation of things. So these are basic part is the problem-specific component. We are not interested here that problem-specific component, because once you design a meta-heuristics, multi-objective meta-heuristics for your problem, so obviously you should concern all the three components. Okay. So next. So first, multi-objective specific components. So for multi-objective specific components, these three things are very much important. That is fitness assignment. Those fitness assignment is basically the part for convergency. So guide the search towards the Pareto optimal solution for a better convergence. Okay? So this is the first part. The second part for diversity preservation, generate a diverse set of Pareto solution in the objective space or decision space. Because we can visualize it in the objective space, but also the main concern is in the decision space, because the solutions are important. And finally, this for elitism, this actually preserve the points in the spectrum, whole spectrum. So next. So there are several fitness assignment strategies. For fitness assignment strategies, some people are considering the scalar approaches, that means the classical approaches, concepts of classical approaches, because classical approaches always gives you a single solution, but that solution belongs to the true Pareto form. That is important. So that means it's very close to the true Pareto form. So if we use that concepts for fitness assignment, that scalar approach or classical approach, that gives you the better convergence. It may be with respect to the weighted sum, weighted matrix, goal programming, epsilon constant, or goal attainment. These are some classical approaches. We use that concept when we design the algorithm for multi-objective meta-heuristics. And also there are some classical approaches which gives you the better performance for diversity. So I will show you in the later on. So then there are some criterion-based approaches. So what are those? That also in the classical based, it may be some sequential approach or some classical lexicographic approach that already I mentioned. And this is very important, that dominance-based approach, because the basic definition of Pareto optimality depends on this dominance concept. So that's why this dominant based, mostly people are using this Pareto dominant concept, but after designing that algorithm by using the concept of Pareto dominance, some people use some other concepts like weak dominance, strict dominance. These are some little difference from the Pareto concept, but these are very simple. Nowadays people are using some fuzzy dominance, because we are considering that uncertainties or randomness in the meta-heuristics algorithms. So sometimes people are using Pareto fuzzy dominance, stochastic dominance, etc. And this part is also very important, indicator-based approach. Initially, I told you there are some statistical components or statistical measure by which we can measure the performance of the algorithm. So for that, statistical measures are mostly based on this epsilon constraint, hypervolume, other types of distance measures, grade, and so on. So I'll discuss it later on. But mostly this fitness assignment depends on different ways. Some are dominance based, some are classical component based, and some are performance measures based. Okay. Okay. So then diversity preservation. So basically here we use some statistical density estimation approach. Statistical density approach, there are different techniques like kernel-based method, nearest neighborhood technique, histogram. So these are some statistical approach. So here in this kernel approach, the concept is we are considering simple Euclidean distance measure. Conceptually, say 1 point, say I am here, which is the farthest neighbor of me. So I have different neighbors. But because we are preserving the diversity, so obviously we choose that neighbor which is farthest from me. Because all are neighbors. So, because if I am selected, so obviously I choose my farthest neighbor. So that's why here the kernel-based approach is simply in this niche, there are many neighbors, we consider the farthest one. It's a very simple concept. Simply by using the distance, Euclidean distance. And what is this nearest neighborhood approach? So I think in some algorithms they use the nearest neighborhood concept. So they divide the whole spectrum by some domain or some niche. So in this domain there may be more than one, but we consider the center one. So which is very close to the center. So again, another domain here, these two are disjoint. So again, in this niche, we consider another one. In this niche, another one. In this niche, another one. In this way, they select in every neighbor one non-dominated solution. Okay. So that is the concept of this k nearest neighbor concept. So every neighbor, there are k points. So by which we can consider single. Oh, sorry. And another is histogram, that is also similar statistical concepts. You divide the whole spectrum in the histogram, and every box you choose only 1 point. Okay. So these are simple statistical approach, but it mainly used for the diversity preservation. So that means out of all those Pareto solutions, we are considering those Pareto solutions which are diverse solutions. Next. And what is the concept of elitism? So for elitism, mostly the multi-objective algorithms, people are considering these archiving policies. So there are some archiving policies. What is the concept of archiving? So it's a preservation policy. That means some of the peoples, they have used only one archive, and some of the algorithms people have used more than one archive, two archive. So what is the concept of archiving policies? So here, by using some meta-heuristics algorithm, you are generating some solutions. So you have a population. So in this population, you have some solutions are non-dominated solutions, some are dominated solution. So every iteration, you are generating some non-dominated solution. So you are preserving those non-dominated solutions in one archive. Okay. So this is your archive. So from your new solution, non-dominated solutions are stored in the archive. So again, new iteration, next iteration, you are generating some new solutions. Again, you send to the archive. So this is a fixed size archive. So after a few generations, your archive is full. So then, maybe you are generating some more better solutions, more better Pareto optimal solution, because what's the disadvantage of these single archiving policies? You are not comparing those solutions which are stored in the archive. Because one iteration you are generating, say, 2 Pareto solution. Next iteration you are generating 3 solutions. So in this way, maybe your archive size is 20, your archive is full. But if we compare those 20 solutions, some solutions automatically dominated by some other solutions. So that is not doing here. So that means after a few iterations, your archive is full and your algorithm is stopped. But then people thinking, so that's why it is called passive elitism. And this is called active elitism. So here they are considering 2 archive conceptually. So you are sending the new solution here and compare within those solutions. If some are dominated, so you discard those solutions. So that means every step you are comparing the solution. So that's why it is called active elitism. So all the iterations you are generating new solution and compare those solution and stored non-dominated solutions only. Okay. So that's why that is the concept, because this is the third point. So we are not considering the solutions which are concentrated some zone. We are considering the solutions throughout the zone. So that means if these archiving policies, active archiving policies are there, so you may consider those solutions which are spread in the whole spectrum. Clear? So that is one way you can preserve it. That means preserve good non-dominated solutions which are diversified. Clear? So this is the 3 things mainly concentrated, mainly when you develop, when you want to develop or when you want to design a new meta-heuristics algorithm. So either of these 3 aspects, any one of these 3 aspects, you have to introduce something new for your model or your algorithm. Otherwise, you cannot claim this is a new multi-objective meta-heuristics algorithm. Is it clear? So that means you should have some innovation, some new things, any one of these 3 components. Clear? So, because already I told you there are 2 important components. One is multi-objective specific component, another is meta-heuristic specific component. If we design a new meta-heuristics algorithm, then your innovation is on that part. Your innovation is not in the part of multi-objective part. Because multi-objective part means it's mainly concentrated on these 3 points: convergency, diversity, and throughout the spectrum. So in this way, generally people are thinking there are many ways you can consider this convergency. There are some classical based approaches, there are some dominant based approaches, there are some indicator based approaches. Okay. So maybe you can design some new indicator or some new statistical measure by which you can improve the solution. Similarly for diversity, similarly for archiving policies. Okay. So these are the steps. Any algorithm, so initialization and other things, this is problem specific component. So here I just consider these 3 different colors. So obviously for any new algorithms for your problem, so once you design a new meta-heuristics algorithm, so you should concern on those 3 points. First is problem specific component. So I have not discussed any problem specific because problems domain is different for different areas. So these 2 are most important here. That is multi-objective specific component. So multi-objective specific component is fitness assignment, diversity preservation, archiving policies. These 3 components are multi-objective specific component. So if you consider meta-heuristic specific component, say for GA, I think you know this selection, crossover, mutation, all those things are there. Selection, replacement, then stopping criteria, these things are important for meta-heuristics. So obviously for any new algorithm, you should frame your flowchart in this way. So first you initialize your problem. So as per your problem definition, then evaluation, then meta-heuristics, fitness, diversity, then replacement, archiving policies, stopping criteria, selection, then next selection, and so on. So within this flowchart, you should. Okay. So I just quickly go through one meta-heuristics, multi-objective meta-heuristics algorithm, how actually this meta-heuristics algorithm works. So most simplest algorithm is NSGA2, but it's huge application in different domains. I just quickly, there are many approaches or many algorithms are available. So I just quickly go through with this NSGA2. So what is NSGA2? Actually, the full form is non-dominated sorting genetic algorithm. It is proposed by Kollam Dev and his group. So in 2002, only one paper. This paper has more than 30,000 citation. Only one paper. So mostly any new paper will come, so they should cite this paper. Anyway, so and this paper he developed in Kanpur IIT, his genetic algorithm lab. Now he belongs to Michigan State University, but this paper is published in 2002, and that time he was in Kanpur IIT. Okay, so so it is NSGA2 is an elitist non-dominated sorting genetic algorithm to solve multi-objective problem. Multi-objective optimization